Good day, everyone. I am Christine May Rodriguez Carnicer, a PhD physics student under the Geophysics Research Laboratory. My research advisor is Dr. Joel T. Makiling. I would like to present my proposed dissertation research. The title of my study will be Geotechnical Characterization and Slope Stability Analysis of Rain-induced Landslides in Mount Diwata, Monkayo, Davao de Oro. So what is my motivation for choosing this research topic? Davao de Oro have been identified as one of the top 20 provinces prone to landslides, mainly due to its mountainous terrain. Barangay Mount Diwata in the municipality of Monkayo in particular is classified by the Mines and Geoscience Bureau or MGB to have high to very high susceptibility to landslides because of its steep slopes and underlying weak materials. Landslides had been a perennial problem in the area, especially during the rainy months of November to March. And of course, rampant mining activities certainly aggravated the situation. Since the early 1980s, people have flocked to the mountain for its high-grade gold ores. Mount Diwata at present is home to approximately 10,000 miners and auxiliary workers and their dependents based from the 2018 census. However, it only covers 672 hectares, or that's a little over 1% of the total land area of the municipality. So this means that Barangay Mount Diwata has the greatest population density among the barangays of Monkayo. In spite of the danger in the area, especially during the rainy season, people continue to live and thrive there because they are dependent on the ore-rich mountain for their livelihood. If the local government unit would strictly adhere to the hazard map provided by MGB, the whole area should be uninhabited. However, this would lead to displacement of people from their communities and consequently loss of their source of income. So this is the current dilemma of Mount Diwata. Since it would be difficult to relocate people from the area, a better way of addressing the problem is to conduct a detailed geotechnical investigation to identify safe locations for settlements. The current hazard map from MGB have been based only on the geological parameters. Thus, the whole barangay had been identified to have very high or even critical susceptibility to landslides. However, a more detailed study on the soil properties and its strength parameters can delineate specific areas as safe and unsafe zones. So, the objectives of my study are as follows. First, investigate the physical and mechanical properties of the soil in the landslide-prone areas. Second, assess the geotechnical properties of the soil to evaluate their contribution to sliding. Third, determine the shear strength parameters of the landslide-prone areas for slope stability analysis and calculation of their factor of safety. And fourth, identify the areas considered as safe zones for settlement and unsafe or no-build zones for possible engineering intervention and monitoring. Despite the millions of pesos wasted from property damages, plus the significant number of lives lost, there had been no comprehensive study conducted yet on the frequent landslide occurrences in Mount Diwata. The current study will therefore be the first geotechnical study in the area and will provide the baseline data for further studies. Note also that there had been no published information on the landslide hazards for the whole province of Davao de Oro, even though it had been identified as one of the provinces most susceptible to slope failures. So this geotechnical study conducted for Mount Diwata can also be adapted to other landslide-prone areas in the province since this area share the common characteristics of mountainous terrain with steep slopes, frequently experiencing heavy and prolonged rains, and the presence of mining activities. So the mechanism of rainfall-triggered landslide often comprise of a complex interaction between hydrological and geotechnical processes, which in turn depends on several factors like topography, hydrogeotechnical properties, and the initial state of the slope. The initial state of the slope is determined by its geometry and the initial water table. However, the actual failure conditions are heavily influenced by rainfall characteristics and the properties of the soil slope. Infiltration is a major factor in the instability of slopes during rainy weather. Rainfall infiltration can reduce matrix suctions or the tenacity of the soil matrix to hold on to water. So this results in the reduction of the unsaturated soil shear strength along the potential failure surface. When the shear strength is no longer sufficient to maintain the stability of the slope, failure occurs. Pore water pressure and water content in a loose soil slope change rapidly. So water infiltration into cracks in the slope has a great impact on landslide development. Geotechnical investigations are carried out to identify the causative factors and landslide triggering mechanism. Soil properties such as particle size and pore distribution of the soil matrix can influence slope stability. These properties influence the rate of water movement and the capacity of the soil to hold water. Soil texture, structure, particle density, bulk density, and porosity are the properties which correspond to infiltration rates. Highly plastic clays with high to very high swelling and shrinkage potential will always favor landslide occurrences. In majority of the cases, the failure mechanism is closely related to the type of material in the slides. The mechanism of lowest landslide is associated to progressive weathering along the zones in these slopes, which causes dramatic decrease in strength. The reduction of shear strength is due to the leaching of readily soluble salts, destruction of cementation bonds, and distribution of particles. However, for rock-soil aggregate slope, the deformation and failure mechanism is a progressive process, and local landslides will occur step by step. The increase in water content decreases its cohesion and friction angle, but this also increases the weight of the upper rock soil aggregate. So the combination of increasing stress and decreasing rock mass material mechanical parameters will result in the toppling failure. Clay, on the other hand, have been characterized by their high swelling potential, sensitivity to humidity, and moisture that it becomes the potential slip zone in an outcrop causing landslide. The abundance of clays in a landslide body has a significant effect on the mechanical properties of the slip zone. The slip zone of a landslide is the natural shear zone resulting from different stress disseminated through different lithologies. Hence, the presence of clay in the hilly region is strongly attributed to landslides. For local studies, the failure mechanism of some of the biggest landslides were investigated. The Ginsaugon landslide in Leyte have been well studied as it is considered as one of the largest to have occurred in the recent years as well as the most devastating in terms of loss of life. According to Evans et al., the occurrence and behavior of the disastrous rock slide debris avalanche was determined by the intersection of geological, tectonic, climatic, and cultural factors. It was initiated by the failure of a 450-meter high rock slope within the damaged zone of the Philippine Fault. The tectonic weakening of the failed rock mass had resulted from active strike-slip movements along the Philippine Fault. In addition, it was further enhanced by undrained loading of rice paddy fields on the valley floor beneath the debris sheet. No direct trigger was identified, but it did follow a period of very heavy rainfall with a lag time of 4 days, and 2 minor earthquakes also occurred on the day of the failure. For the study of Catane et al., the September 2018 Naga Cebu translational block slide occurred as a multiple block detachments along a series of tension cracks that formed and grew progressively prior to the main failure. Preliminary slope stability analysis showed that the slopes were marginally unstable even in dry condition. Though the low angle profile of the slip surface favors stability, but the low shear strength of the limestone bedrock and unsupported cut slopes may have contributed to the failure. There was no apparent direct trigger for the landslide, so this implies that a marginally stable slope can stand for several years before failure occurs. Several landslide susceptibility maps on different locations were also made employing statistical analysis to determine the causative factors for the slope failure. Landslide inventories were performed using aerial photographs and satellite images. Dumlao and Victor, applying logistic regression within a GIS environment, showed that almost 40% of Antipolo City is potentially high risk in terms of landslide incidents. The logistic regression model developed by Cruz et al. For Benguet identified aspect, elevation, and leaf area index as the causative factors which have statistical significance to landslide incidents. Their model also showed that 69% of Benguet is highly susceptible to landslides. Opiso et al. Also used GIS and frequency ratio to evaluate the causal factors of rainfall-induced landslides along the Cagayan de Oro, Bukidnon, Davao City route. Frequent landslides had hampered the flow of transportation in the area. The rainfall-induced landslide susceptibility index map generated showed rainfall coupled with soil type and slopes were the main triggering parameters. The deterministic GIS model, called Stability Index Mapping or SINMAP, was used by Alejandrino et al. To generate a rainfall-induced shallow landslide hazard map for Davao Oriental. SINMAP used a digital terrain model to derive topographic, soil geotechnical, and hydrological parameters to compute for the factor of safety. The landslide susceptibility classification was translated to zoning maps indicating areas that are safe from shallow landslides, areas that can be built upon with slope intervention and monitoring, and the no-build areas. So this study showed a great improvement from the MGB release hazard maps, which only utilize geological parameters and usually renders all steep slopes of the mountainous area to have critical to high susceptibility to slope failures. And finally, the intensive landslide assessment and susceptibility maps carried for Kibawe Bukidnon included an intensive field sampling utilizing around 20 boreholes. So the result of the study revealed that the area have mostly inorganic but highly expansive fine-grained soil. It was also noted that the factor of safety has a considerable decrease when the slope condition change from completely dry to fully saturated. The findings of the study provided a baseline reference for the area's slope stability that will be applied in land use planning and future development. Hence, it can be inferred from all this literature reviewed that slope movement occurs when forces acting downslope, mainly due to gravity, exceed the strength of the earth materials that compose the slope. So a landslide is mainly caused by factors that increase the effects of downslope forces and those that tend to reduce the strength parameters of the slope. The oversteepening of the base of the slope due to natural erosion or excavation, or the increase in the weight of the slope itself because of water inflow or some load can increase these downslope forces or shear stresses. The reduction of the slope material shear strength, on the other hand, are primarily defined by its frictional and cohesive strength. Frictional strength is the resistance of the slope materials interacting constituent particles to movement, while the cohesive strength corresponds to the bonding between these particles. In this study, the factors affecting rain-induced landslides will be primarily the soil properties and its strength parameters. The soil type will dictate their engineering behavior, especially in the presence of water. Hence, the knowledge of the soil type and particle size distribution of the failure material in a landslide is important for a better understanding of its failure mechanism. The consistency of a fine-grained soil is also largely influenced by the water content of the soil. Gradual increase in water content of a fine-grained soil slurry causes the soil to pass from the liquid state to a plastic state, semi-solid state, and finally to the solid state. The water contents of these changes of state are different for different soils, and so the strength, consistency, and behavior of the soil are different for each state. Hence, another soil property that needs to be evaluated are the consistency limits or the Atterberg limits. Soil permeability or porosity is also measured to assess drainage characteristics of soil. For the soil strength parameters, the angle of friction and cohesion will be determined to calculate for the slope stability in terms of the factor of safety. The first step in the proposed methodology is the selection of the locations for the collection of soil samples. Locations for soil sampling are chosen based on previous landslide events provided by MGB reports, as well as the recent landslide hazard map of the area. However, reconnaissance site visit and consultation with the locals will still be conducted. Test pits are utilized for the collection of soil samples because aside from being the most economical and efficient, given the steep slopes in the area, they also allow a direct inspection of the soil strata. Disturbed samples will be taken from the moved mass as well as from the unmoved side scarp and head scarp zones. Undisturbed samples, on the other hand, will be taken only from the side and head scarps. The sampling depths will range from 0.5 meters to 1 meter. So these depths are representative of soils involved in the landslide since, according to the MGB reports, the mass movements are superficial and shallow slides. Intact or undisturbed samples will be taken by manually inserting a metal tube, called the Shelby tube, into the soil. The following laboratory tests will be conducted: particle size analysis, soil classification, natural moisture content, Atterberg limits, soil permeability or porosity, and direct shear test. The particle size analysis of soil covers the quantitative determination of the distribution of the particle sizes in soils. The distribution of particle sizes larger than 75 micrometer is determined by sieving, while the sedimentation process is used to determine the distribution of particle sizes smaller than 75 micrometer. The experimental setup consists of sieves with varying mesh diameters, and these sieves will be arranged in descending sizes from top to bottom. A mass of dry soil sample is placed on the top sieve. The top sieve will be covered with a lid and a pan is placed at the base of the bottom sieve. So this entire assembly is then shaken either manually or in a machine known as a sieve shaker. Shown here is the data for the particle size distribution of the soil sample in one of the sampling sites, Purok 22. The mass of the soil retained on each sieve is measured and recorded. So this is the cumulative mass retained in the table. Its percentage relative to the mass of the soil on the pan at the base is also calculated. From this, the percentage of the soil passing through each sieve is determined by subtracting the percentage of the soil retained in each sieve to 100%. So this is the last column. So this percent of soil passing is plotted versus the sieve sizes. The sieve sizes will be in a logarithmic scale. The resulting graph is known as a particle size distribution curve. So this curve forms one of the most important index properties of the soil. It will show whether the soil is uniformly distributed or it has a well-graded distribution. A smooth concave represents a well-graded soil. So in the resulting graph, it would tell us that we do not have a well-graded soil. The percentage passing in number 200 sieve is used to identify whether the soil is coarse-grained or fine-grained. So it is coarse-grained if the percent passing is less than 50% and fine-grained if the soil is greater than or equal to 50%. So our data tells us that the soil sample is fine-grained and so it is composed of mostly silt and clay. Atterberg limits are the basic measure of the critical water contents of a fine-grained soil. Depending on its water content, a soil may appear in one of the four states: solid, semi-solid, plastic, and liquid. In each state, the consistency and behavior of a soil is different and consequently, so are its engineering properties. Thus, the boundary between each state can be defined based on a change in the soil's behavior. The plasticity index is defined as the range of moisture content over which the soil deforms plastically. It is the difference between the liquid limit and the plastic limit. So the plasticity index is a measure of the plasticity of a soil, and it determines the amount and type of clay present in the soil. In general, soils with high plasticity index tends to be clay, and those with lower plasticity index tends to be silt. And those with a plasticity index near zero tend to have little or no silt or clay present. In the study, the fall cone method is used to determine the Atterberg limits. So the soil used in this test are those that pass the 425 micrometer, or that's number 40 sieve. In this test, the liquid limit is defined as the moisture content at which a standard cone with apex angle of 30 degrees and mass of 80 grams will penetrate a depth of 20 millimeters in 5 seconds when allowed to drop from a position of point contact with the soil surface. Since it is difficult to get the soil moisture content for the exact depth of 20 millimeters, 3 or more tests are conducted for different moisture content, and the corresponding depth that the cone will pierce the soil are recorded. So here is the result of the Atterberg limits test on the preliminary soil sample. So table shows 4 trials for the moisture content and cone depth for both liquid and plastic limit. A semi-log graph can be plotted for moisture content versus the cone penetration depth. The plot results to a straight line, and the liquid limit will be interpolated from the said plot. That is the moisture content of the soil for the cone penetration depth of 20 millimeters. So the liquid limit and plastic limit are determined from the resulting graph of the moisture content versus cone penetration depth. So from our plot, we therefore have a liquid limit equal to 41.5%, plastic limit equal to 25.47%, and so the plasticity index, the difference of the two, is equal to 16.04%. So these values tells us that the soil is moderately plastic, so its composition is silt and clay, and it is not cohesive. Shear strength is defined as the maximum resistance that a material can withstand when subjected to shearing. In soil mechanics, the shear strength is evaluated using the Mohr-Coulomb failure criterion, and it assumes that the shear strength depends on 3 factors: the normal effective stress, the friction angle of the material, and the cohesion of the material. So the direct shear test is considered as one of the most common and simple tests to derive the strength of a soil and can be performed on undisturbed or remolded samples. The test equipment consists of a metal shear box in which the soil specimen is placed. The soil specimen may be square or circular. The box is split horizontally into halves. Normal force on the specimen is applied on the top of the shear box. Shear force is applied by moving one half of the box relative to the other to cause failure in the soil specimen. So depending on the equipment, the shear test can either be stress-controlled or shear-controlled. The direct shear apparatus used in the study is strain-controlled. So in a strain-controlled test, a constant rate of shear displacement is applied to one half of the box. The resisting force, shear force of the soil, corresponding to any shear displacement, is measured. So the table and graph shows the resulting shear force for any given horizontal displacement. So note that as the displacement is increased, as expected, the horizontal force also increases. But after the displacement of around 4.75 millimeter, the shear force is already maintained at 15.2 newtons. So this therefore corresponds to the maximum shear force, and we can now calculate the maximum shear stress as shown. So for this trial, we therefore have a maximum stress of 61.3 kilopascal. So three trials are made to allow us to plot the normal stress versus shear stress graph. So from the graph, we can determine the cohesion and angle of friction following the Moore-Coulomb failure criterion. So these two soil strength parameters are important for soil stability analysis, in particular, the calculation of the factor of safety. So the factor of safety allows us to evaluate whether a given slope is stable or unstable. So in conclusion, my proposed study will utilize the geotechnical properties of the soil samples from the landslide areas in Mount Diwata to evaluate the stability of these slopes and identify which particular properties contributed to these slope failures. So this will be the end of my presentation. Thank you for your time and attention.